Okay, good morning. So I'm going to end this week, good morning, with just a couple of different results, some of basic results, but then at the end I'm going to talk about two of my favorite problems in a little bit more detail. I think there are two very nice problems, but also they are fairly open, so there's quite a lot of work remaining to do on those problems. So, but they might be a bit tricky. Okay, good. So I'm going to get back to what I was showing you yesterday, the popular place problem. So again, just to restate the problem, we're given n moving entities in the plane. We get a positive integer, and we got a positive real value. And the question I'm asking is there an axis-aligned square, say sigma, of side length at most r? And we say that this is a popular place if there is at least k entities visiting it. Okay? So I have to, since I did the animation once, and it takes a long time to do the animation, I'm going to run it over and over again until you get tired of it. So here we have 5 of them visiting. So if k is smaller than or equal to 5, then this specific square is a popular place. Okay, and there are two models again, just as we've been talking of most of the problems this week. There is a continuous version. So sigma is a popular place if it's intersected by any part of the trajectory, right? So it does not have to contain a vertex of the trajectory. While in the discrete model, we require that the popular place has to contain a vertex of the trajectory. Again, the continuous model is much more general, and it allows us to use, for example, simplification. However, in general, the continuous model is much harder to handle. But I think at the end it's a much more useful model. Okay, and the result for this problem is that if we want to find a maximum number of visitors, then you can do that in roughly quadratic time. I'll just show you later on how this is done. It's a very simple algorithm. And the discrete version, you can do it much faster. You can do it in tau n log tau n. And the lower for both these problems, the bounds are tight. So you cannot do any better than this. And yeah, so I'll show you the continuous version. It's a very easy algorithm. So for many of these problems, the question is, what do you want to report? Right? Should we just detect if there exists a popular place? So more or less a decision version. Or should we report all the popular places? Or should we report a popular place with the maximum number of visitors? Right? So it's the optimization version. Or should we just say, let's report all of the popular places? So what I'm going to do here is I'm going to just report all the popular places. Because I think it shows a little bit of the property of the problem. Okay, so let's look at this problem. So this is my trajectory. Say I only look at one trajectory at a time here now. And then I take a square of radius r, so that could be my potential popular place. And I put the center of this square at the start of the trajectory. And now I just sweep the square along the trajectory. Okay? So this will trace some region around my trajectory. Right? It will cover this area. Okay, and let's it doesn't matter if I visit the same place twice, so the depth does not really matter. It's just if I visit it or not. And of course, if I look at a popular place, any popular place, with the center inside this union, then the trajectory has to intersect the popular place. Right? So if I put the center of a popular place inside this union, then this trajectory visits it. So that indicates a very simple approach. Right? So then the problem can be stated as follows. Given a set of polygons with holes, find a point that stabs the maximum number of polygons. Right? Because you can see each of these trajectories as a polygon. Right? And now I just take the set of all these polygons. And what I want to do is find all the points for which that lies in at least k different polygons. Okay. And you want to maximize this, then you will just take a point that lies in a maximum number of polygons. Okay, so maybe we have these 3 polygons. So that corresponds to 3 trajectories. So one of the standard algorithms in computational geometry is just sweeping the plane. So what do we want to do? Well, we want to find all points for which there are k polygons that intersect it. Okay, and this can easily be done using a sweep line approach. So we just sweep a vertical line from left to right while maintaining the number of polygons that intersect each face in this arrangement. So we sweep from left to right, we stop at each vertex or each intersection point, and then we just compute the depth, so the number of polygons that intersect that face, and then when we've done that, we just continue. Okay. And of course, when you get to a new face, the only thing that happens is that the number of polygons go up by 1, it stays the same, or it goes down by 1. So it's a very simple approach. So we just continue through all the handle each vertex as a separate event. Okay? And okay, come on, do the sweep. And of course, we also have to handle all the intersections, because again, there you could have a change. So there are n square events, right? And sorry, how many events are there? Yes. So I have n polygons. Each polygon has tau segments, right? Order of tau segments, and I take the arrangement of all those, so I get order n squared tau squared. Okay. The complexity of this. So if I just do this naively, then the running time is, this should be taus, but this would be tau square n square log tau n. Right? And the amount of space I use is tau squared n square. However, if you look at the problem a little bit, you can see that you can just use an old idea by Edelspun and Gibas. It's called topological sweep. And that improves both the running time with a factor of log tau n and also space. So you get a small improvement. Okay, this is a standard tool, so I'm not going to show you how to do this, but okay.
So why do you need tau squared and space?
Because so I look at the let's see, why do I need tau squared space? Because, well, the complexity of one trajectory, if I trace the trajectory, I have tau segments, but these can intersect, right? So the complexity of that is tau squared.
Yeah, but couldn't you just take simply all the lines through that and compute, so you compute too much?
Yes, but also you mean I don't look at the union, I just look at the, yeah. So, okay, this was 2007, but the problem is that I want to look at the depth, right? So I want to look at the number of different colors that I hit.
Yeah.
So I don't want to go in and look for if a color is there or not. So, yeah. Okay, good. So the problem is then just find the maximum color depth using topological sweep, and this has been done by Gibas and Edelspunner. Okay, actually this should still be tau squared, I think. Okay, so actually we had a student implementing this, and it works, but as very common when you implement geometric algorithm is that it's very hard to handle degenerate cases. So he actually had to spend a lot of time just handling all the degenerate cases, which is a bit of a pity, but it worked out at the end. And also the problem has a tau squared n squared lower bound. So this is how the final result looks. So these are all the polygons for which every point inside defines the center of a popular place that has at least k trajectories visiting it. And you can see it's not very fast, right? So we had 32 trajectories. Each trajectory has 1,000 timestamps. And even if we use the simplification of the path as a pre-processing step, which you can do, right, because we're using the continuous model. Because we use the continuous model, we can do the simplification and then run this algorithm. Good. So in the discrete model, we can do it in tau n log tau n. And in a continuous model, we can do it in tau squared n squared time. Okay. Good. Okay, so let's any questions about the popular place? So again, there is variance where if you want to report the maximum, or you want to just report sum, then you get different variance and different running times. But for report all, these are the results. Okay, so the second problem for today is segmentation. So this is a problem where you want to so you get your trajectory, and now you want to detect sub-trajectories of that trajectory that have where all the points have similar attributes. Right? So this is very often used by behavioral qualities where they want to automatically detect, for example, when the bird is doing so-called transport flights. So when they migrate, they have very long flights, and usually it's very directed, and they don't stop very much on the way. And for example, you would like to detect the time intervals where a bird is foraging or playing or whatever it could be. And you don't want to do this manually, so you would like to do all this automatically. Okay, so what we get is a trajectory T, where each point has a set of attribute values. And then we also get a set of criteria. Right? So these attributes, they could be anything, but let's say it could be, for example, the speed, the heading, the curvature at that point. And the criteria could then be that we want to find a sub-trajectory where the speed is more or less constant during that sub-trajectory. Or at least that it doesn't vary too much inside that sub-trajectory. So what we want to do is we want to partition T into a minimum number of sub-trajectories. And they're called segments, so it's a little bit tricky. Such that each segment fulfills the criteria. So an example. So here is we're given as input the trajectory in the top left corner, and say that the coordinates of this entity is measured with regular intervals, say every minute or so. So that means that the length of an edge is actually corresponding to the speed. Okay. So look at the top right one. So top right, there we say, for example, the speed cannot differ by more than a factor of 2. Okay. So then we cut the trajectory here, and in this area here, all the edges are the same length. So that means that the speed is more or less the same. Here, again, all the edges are of more or less the same length, so again we get a new sub-trajectory, a new segment, and at the end, he's very slow, and we get a new sub-trajectory. So you want to find the minimum segmentation for which this holds. So that's why I was talking about the simplification. I mean, this is kind of related to simplification. Bottom left, here I want to do segmentation with respect to heading. Right? So again, say that the direction of motion differ by at most 90 degrees. So this is a typical directed flight when you do migration, for example. That the bird more or less flies in the same direction for a very long time. So again, the bird is flying in the same direction, and when you start to turn too much, you cut it. And then you continue, cut it, and you continue, cut it, and there you see there are a lot of changes at the very end. So you get a few more segments. And finally, this one. No. One, two. Okay. So the final one, you can use a conjunction of both of them. Right? You can say, I have a requirement, I have a constraint on the speed, but I also have a constraint on the direction. So you can take the conjunction and disjunct them with any kind of attribute values. And I'll show you an example later on where I do this. Okay.
Sorry,
Yeah.
are the location of the vertices on the curves are defined before? I mean, what is the role of these attributions?
So the attributes you have on each point. So this is so when you measure. So let's say it's different depending on the values. But for example, I might have instantaneous speeds on all the points. So then I say maybe I want the speed to be bounded within this region. Or I could have a temperature. So for example, when you track geese, you actually get the temperature too. So then you can say, I would only like to look at the trajectories for which it's warm. I don't know why you would like to do that, but
Maybe I'm confused because according to the segmentation, I thought that there is a trajectory and we want to segment, find the segments, find the location of vertices on that according to the attributions, but it seems that it's not.
well, so the requirement is that if you look at the sub-trajectory, the segment, right? So let's look at this segment here, for example, right? Then for all vertices in that segment, they have to fulfill the constraint, right?
You mean those squares shows the end and the start and end of each segment?
Yeah, exactly. So I cut it here, right?
Okay, not those other vertices.
Now those are just my the vertices that I get as input. Yeah. Yes. Yes. So I want to partition it, right? So that means that when I partition it, two consecutive segments will share a vertex, right? This is the start of the first segment, this is the end of the first segment, but this is also the start of the second segment. Okay, so we want to segment the trajectory into segments or sub-trajectories according to its behavior in that segment. And there are two versions again, but more or less all the available results are only for cutting at vertices. I mean, you could imagine cutting at the middle of an edge, for example. But I will only consider cutting at the vertex. Okay, so partition a trajectory into a small number of segments such that the given criterion is fulfilled on each segment. So you just cut. And you get a few pieces, and for each piece it has to fulfill the criterion. Okay, so here, for example, it could be that for each segment you have a bound on the heading. Okay. But again, there are a lot of different criteria, right? So heading, speed, you can say location. The entity is not allowed to move too far away from a specific location. That could also be a criteria. Could be that you have a bound on the curvature, the sinuosity, and then, of course, any combination of these. And I mean, in principle, you could just take any criteria. Right? The problem is, of course, can you compute all of them? Okay. So a criterion is decreasing monotone if it holds on one segment, it holds for any subsegment. Okay. So, for example, if I look at, let's say I have this is my. So say that this is my a segment. Right, say this is T1 to TK. And say that within this segment I have a bounded heading. So all of them fly in this direction. They all move in this direction. Okay? So now, of course, if I take a sub-segment, then it's still true, right? Because if I take this and this, for example, Ti and Tj, then this interval will be even smaller for the segment starting at Ti and ending at Tj. Right? So that's why it's called decreasing monotone. Right? The nice thing is that so I just have to look at this larger interval. If it holds for the larger interval, I can just cut it. I can just do, say, the binary search on it, for example. Right? So that's the decreasing monotone. What about increasing monotone? So there I say if it holds for an interval Ti, Tj, then it will hold for anything that is bigger. Right? So of course I can look at all of these in combination. So we ask the question, does it make sense to look at increasing monotone by itself? So say I only have one single function that is increasing monotone. Does it make sense to look at that by itself?
Besides segmentation, such an issue doesn't really make any sense because we can expand our sub-trajectories and have another.
Yes.
So in decreasing monotone, we have another segmentation there.
Yes. So for increasing monotone, I mean, either it holds for the whole trajectory, or it doesn't hold at all, right? So you could just check the two endpoints, check if it holds. If it holds, we're done. If it doesn't hold, well, it doesn't hold for any sub-segment either. So, okay. So if you only look at very simple criteria, so say it's only decreasing monotone, then we can just use a greedy strategy, right? So we can go from the start to the end and just for each point decide if it is valid or not. So we test the first segment, the second segment, the third, and so on. And we continue just until it doesn't work anymore. Okay, so we cut there, and then we continue from there. So for many decreasing monotone criteria, this just takes linear time. Right? So for example, if I want, say, heading or speed, then adding a new vertex will only cost me constant time to update. Right? So I can, if I check this, just adding this one, well, it only costs me constant time to check. So that means running this greedy algorithm will cost me linear time. In some cases, it might be better to do some kind of binary search. So I just exponentially double. So I do my search first of one segment, then two segments, one, then three, then I double, and I double. And then when I found a miss, then I do binary search in that interval. So that means I only have to perform log n queries for each segment. Right? So if I have a segment of length k, then it will only cost me log k queries to find it. While in the greedy algorithm, I would actually have to pay order of k queries to find it. Yeah?
Doesn't this algorithm depend on the output, because you might have O n size output, so how can you achieve it in log n?
Now log k times the number of segments you get. It will cost you log k, so it will cost you a logarithmic factor for every part of the segment. Yeah. So you're right. So if I get a linear number of segments, it will cost me say n log n time. Well, actually, it won't, right? Because then this will only cost me constant time because I will immediately be able to say no, I can't do anything. So it only costs me. So then will be linear again, I guess. Okay, so the nice thing is that you can actually handle a combination of decrease and monotone criteria using this. And again, you can do it either by pure greedy, or you can do some kind of exponential on it and binary search. Yeah? Yeah?
What does TI work?
Sorry, this one?
T0 till yes. What does tau do?
So it only asks, so I look at the subpath between T0 at the time T0 and Ti. And the only thing I ask, does this subsegment, does this segment fulfill the criteria or not?
For example, if the criteria the speed between 2 points, it has to check all of the points. So all of the points between T0 to Ti.
So it depends on the criteria, right? So, for example, if I'm only interested in, say, speed, then I will have to go, if I have done no preprocessing at all, then I will just have to go through the speeds of all the vertices and say what is the maximum speed, maybe, or minimum speed.
So my point is, maybe this algorithm costs more because if you would do it in linear time, in linear each by each, so it will be much faster. And if your criteria just depends on the first point and the last point, maybe when you double your distance, you
yeah, I know. I understand what you mean.
cross the point that the change happened. So, for example, if you have a trajectory like this, you start from here and you want to check where you change your weight. So maybe you go here, here, and then you cross this point and you go up there, and so you miss this point.
Yes. But remember that now we're only looking at monotone criteria. Right? So maybe you miss it. So you go here, you miss it. But then you continue to do binary search inside here. And since I know if I look at the last point for which it holds, I know it will hold for anything that comes before. Yeah. I mean, so it works very well for decreasing monotone criteria, but it's also very weak. Right? I mean, this is a very strong constraint on the function. Okay. And of course, it depends fully on how much time it costs to actually perform the test. Right? I mean, some of these tests could be more or less constant time, while some tests could take a very long time. Right? So I'm just saying how many times you would have to test it. Okay, but so this was for decreasing monotone. And even if we put some very simple increasing monotone constraint on it, or criteria, then we see that the greedy algorithm doesn't work, which is kind of obvious. Right? But so, for example, if we have that we want the minimum duration to be 2 and the max speed to be vary by most 4. Right? So the range of the speed should be between, say, 1 and 5 in this case. And a segment has to contain at least 2 edges. Well, then the greedy would start from here and it will go up here. And that would be the first segment. And then there's only one segment left and it cannot do anything. Right? While there actually exists a solution, which is just to go up to 3. So that will be your first segment. And then the second segment will be the 2 vertices. Right? So it just says that if you use greedy for any kind of criteria that is not only decreasing monotone, then you can have problems. Okay, and just to illustrate this a little bit more, so Michael Buchin and some other people did a study on geese migration. So Mike is a computer scientist, but she did a small project with a behavioral ecologist, Andrea. So just to show you the application. So they track geese, and they have 2 behavioral types. One is stopover, and one is migration flight. So this is for migrating birds. And the only thing you want to do is decide when they stop to rest and when they're flying. So it seems trivial. But usually this is done manually, right? And now we just want to have an automated tool that does this for the behavioral ecologist. Okay, and it's a GPS track. And then also what they did was they had some tracks where the behavioral ecologist did the annotation, and then they had some tracks where they actually computed it automatically. Okay, so apparently they migrate in the spring. Who knew? And they have roughly up to 10 stopovers during the migration. And this is how they define it. So it's a very crude definition, but it seems to work well. So they say a stopover is at least 48 hours. Right? And it is within those 48 hours, the bird has to stay within some kind of bounded area. That's a stopover. So you see, it's a very simple definition. And when you're flying, well, then you have kind of a migration flight. So you say, well, we don't want the bird to change too much, because the bird actually has a target, right? So the bird is flying very much focusing on that target. So you want the heading to be less than 120 degrees. So this was the result I got. And if you study it, this actually works pretty well. But I mean, it's a fairly simple criteria, but it seems to work very well. you get most of the stopovers, so the stopovers are the red ones. And you see there are some local differences, but in general it finds all the stopovers. Again, here you have several stopovers, and that's found by the algorithm. Here again, and then you get some when you're getting closer to the endpoint. But again, if you have thousands of these trajectories, it is a pretty nice thing to be able to do, to run this algorithm and get all this information automatically instead of going through all these trajectories manually. But as you can see, even something very simple like this is not decreasing monotone, of course. Right? So this decreasing monotone seems to be way too restricted. Okay. So maybe a first step would be to look at a combination of decreasing monotone and increasing monotone criteria. Right. So here we say, for example, so this is a decreasing monotone. Right. If you take a subsegment, then it will still stay within a circle of radius 30 kilometers. This is increasing monotone, and this is this is decreasing monotone, and this is increasing monotone. Right? If it holds for one segment, it will hold for anything that is bigger than that. Right? If you look at only the 48 hours. Okay. So then Aronov et al. Just recently, last year at SODA, they introduced something called the start-stop diagram. So what they do is they take the input trajectory, they put it into what they call a start-stop diagram, which actually has similarities to the free space diagram. And then from the free space, from this start-stop diagram, they compute the segmentation. And I'll show you how this is done. So we're given a trajectory t over time and a criteria c. Okay. So the start-stop diagram is the top left triangle bounded by the diagonal of this n by n matrix. Okay. So again, each cell here is associated with an edge or a segment. So this means that I look at segment starting at 1 and ending at, say, 5. And I'm just saying, is this a valid segment or not? If I look at this segment, does it fulfill the criterion I'm given? Right? So again, it's just a yes-no. Right? Either I fulfill the criterion or I do not fulfill the criterion. So it's very simple. Okay. So ij is in the free space if C holds on Ti, Tj, and ij is in the forbidden space of C if C does not hold on Ti, Tj. So yes, no, again. Yeah? For the discrete case, yes. Yeah. So I'll get to that in just the next slide, actually. Or maybe I removed it. Okay, so for the general case, when you can cut anywhere, it was shown that it's NP hard. Yeah. And I mean, it becomes a little bit tricky, this. So that's why I decided to only do the discrete case. But it is possible to do in the continuous case. But there are no real good algorithms to handle it. So that's a nice open problem.
So what's open if it's NP hard?
Well, the question is, could you approximate it? So the problem that is NP hard is find the minimum number of links that forms a segmentation. Right? So you could say, maybe I can compute a 2 approximation. Or also maybe you can restrict the criterion. so that you can do it fast in certain cases. And that's exactly what they do also. Yeah? So finding a minimum link in finding a minimum link path in a simple polygon with holes is awfully hard. Okay, so a minimal segmentation of T corresponds to a minimum link staircase in D. So I'll show you how that looks. So say we have a trajectory containing 12 vertices. And now I build the start-stop diagram. Okay. So now the statement says that a minimal segmentation of T corresponds to a minimum link staircase in D. Right? And this staircase has to go to the diagonal of this diagram. Right? So that means if I go from here to here, that means that the first 6 vertices form a segment. Right? Then I go, of course, so because I cut it at 6, that means that the next segment has to start at 6. So I go to 6, it has to start here, and I go and find a white space. So that means I can go to 9. So the second segment is 6 to 9. Then I start at 9, and I can go to 11. The third segment is 9 to 11, and then the last one is just 11 to 12. Okay. Yeah?
If you start with a continuous trajectory, is it good to minimize segmentation?
If you start with a continuous trajectory. You mean just in general, if it's good? Or? So I think it's a nice tool to use to identify sub-trajectories that are similar in some sense. I mean, this is what the biologists asked us for. So in that sense, I think it's good. Yes.
It's not very good similarity, minimize segmentation.
So the minimized segmentation, of course, is just to see to it that you don't get too many of them to handle. Right? I mean, if you do the segmentation and just cut everywhere, that will give you a valid segmentation, but it doesn't really help you very much. Yeah. Yes. But I think you're right. I mean, it would maybe be interesting to say that can you do a segmentation where each segment has a minimum length, for example, or something like that. Okay, so in this case, this staircase would correspond to this segmentation. Okay. So how would we compute this? Well, so you can either do a fairly simple dynamic programming approach. So you more or less say, well, if I want to go to the top right, well, that's the same as going using one link to all the previous ones I can reach, and then the optimal solution for all those subproblems. Right? Another way to look at it is just that you can build a graph, right? So here, for example, 1 can reach 5, 6, and 7. So you take 1 can reach 5, 6, and 7. Then 5 can reach 6, 7, 8, 9, and so on. So you get a directed acyclic graph. And now you just find the shortest minimum link path in that graph. Okay, so since the number of edges could be quadratic, and then I do a breadth first search, this will take me quadratic time to compute. Okay. Is that clear? Good. And then I just find the shortest minimum length path. And this was, again, shown by Aronov et al. In last year. So they also proposed a variant. So they wanted to, so the problem is now we started with decreasing monotone. Now we have increasing and decreasing. But is there anything you can say, can you say something more general in a sense? And that's what they attempted to do by defining a stable criterion. So they say a criterion is stable if and only if the number of changes is bounded. Right? So you look at a segment, and maybe it's true for that segment. Now you start to increase it, and maybe it will become false. Now you increase it, it became true again. And now it might be false, true, false, true. And there's no real bound on this, but you could actually say, well, it can happen any number of times. But if you bound this number by a linear number, then you can actually do something. Okay. So first of all, the observation says that if you have a decreasing and increasing monotone criteria, they are stable. They're always stable because they will just change once for each index, right? So it's true and then it's not true. Well, that's fine. Okay. So a conjunction or disjunction of stable criterion also stable. Well, this is pretty easy. You can just look at overlaying them, and everything that is not true will be not true. So it will be the same bound. Okay. So the main contribution in a very recent paper is that you can take your matrix, which usually takes a quadratic time to compute, and you can use a compressed version of it. So you use run length encoding. So it's a very simple idea, right? So this one says, okay, everything from left to right up to, say, index 9 is not valid. So instead of actually storing it bit by bit, I just say, okay, the first 9 is not valid, and then the remaining 3 are valid. Here I say the first 7 are not valid, and then the remaining 4 is valid, and so on. Okay, so let's look at the just decreasing criterion, and we want to compute the longest valid segment. Okay, so we have a criterion C and we have a trajectory T, and what we can do now is just move 2 pointers, I and J, from the back to the front. And we can just, for every trajectory index J, we just compute the smallest index for which the subsegment, the segment, satisfies the criterion C. And then we just store that in our array. Okay. Good. So this, of course, requires a little bit of additional data structure, but it's fairly simple. So you need to just check if it's valid or not. You need to be able to query it. You need to be able to extend the segment. And these are all very simple operations that you can perform with a binary tree. So you can do this in n times C times n, where C of n is the time to update and query. So again, it's very easy to do. And of course, you can do exactly the same thing for increasing criteria. Right? So I mean, one simple way to see how would you do it for increasing criteria? Well, you can run the same algorithm, but you could also just negate the diagram. Right? Everything that is forbidden will be white, and everything that is white will be forbidden. Okay. So the nice thing with this is also that if I look at the start-stop diagram and I look at the conjunction or disjunction of several criterion, of two stable criteria, then the intersection is, if I take the conjunction of two stable criteria, then I just take the intersection of the two start-stop diagrams. Right, so if this is one criteria, and then I just take the union with the other one, and I immediately get the conjunction of both of them. Okay. And as I said before, actually it does not really cost me much to do compute the compressed version. Right? So I can more or less do that in linear time. So I don't have to compute the whole matrix. I can just store it in a short version. But yeah, let's. So there are a lot of examples of stable criteria. So you can have some lower or upper bounds on the criteria. So just say, for example, it has to be at least 48 hours. You have to stay at least 48 hours. Or the speed has to be at least 20 kilometers an hour, or whatever it could be. You could have some angular range criterion. So I have to head in this rough direction during the whole segmentation, or the whole segment. I can have disk criterion. So again, I'm not allowed to, if I come into the area, I have in the next 48 hours or so, I have to stay within this area. And I can even allow a fraction of outliers, actually. So, for example, if this guy goes out a little bit and then comes back, well, that's okay, as long as that doesn't happen too often. Good. Okay, so again, if we want to compute this, it's actually a very simple dynamic programming algorithm. It just says the optimal segmentation, if I want to go from the start to, say, segment I, is either one segment. I can go directly from 0 to I, so that would be just one long segment. Or, or an optimal sequence of segments from 0 to j, and then one segment between j and I. Right? And of course I can do this for every I and j. Right? So that immediately gives me a quadratic time algorithm. So that's very easy. If you want to use the compressed matrix, you can actually do even better. And I'm not going to talk about it, but it's not very hard to see that if you just use this and a little bit of data structures here, you can do this in n log n time. Again, I should say that even if now they try to extend this, so it holds for any stable criteria, it is still very restrictive. Right? So would it be possible to extend the criteria you can handle? Or can you do something else? Okay, so just to summarize, so you can do the greedy algorithm for decreasing monotone criteria, and you can do it either in linear time or in log n time. I showed you a case study of the geese migration. The start-stop diagram for arbitrary criteria you can do in quadratic time for the discrete case. And now there is a very recent improvement, so this is actually unpublished. Or it's published as a master thesis. Where they improved this to n log n time. So what do you think, Shervin? Is it similar to any simplification things you've done?
It's a different problem, but related.
Yes.
The question you asked, something, yeah, you can use on.
Yeah, I think there is a strong connection here, right?
Yeah.
Yes. Good. So now the last half hour, I'm going to talk about two of my favorite problems that I think deserves a little bit more. I think especially this one boils down to a very nice geometric problem that is very easy to state. So what it originated from is that you want to find some kind of repetitive behavior from an entity you're tracking. Right? So, for example, if you're tracking animals, maybe they will go to a lake every day to drink. And in a sense, you want to track this repetitive behavior, this regularity in their movement, right? So maybe they would go every day, or maybe every month, or maybe you have some kind of annual migration, or whatever it could be. But it doesn't have to be doesn't have to be like every day, right? I mean, for example, if you do sports or something, sometimes you maybe don't have time, maybe you're injured, but still it's a regular occurrence, right? So maybe you go 75% of all the time. Well, that should be detected in some way. So then you can model this in a very simple way. Say that you have the area you're interested in, right? And now, so you can say, well, either I'm in or I'm out. So I mark all the intervals where I'm inside. And every time I'm not inside, well, then I'm outside. And notice that here you could actually do this for anything, right? I mean, this is not... it doesn't have anything to do specifically for trajectories, right? It could be when either the traffic signals are on or they're off. Either your professor is wearing a red T-shirt or not a red T-shirt. Okay. So now you want to try to find some kind of regularity here. So you want to find regular events for which at each event you're inside the interval. Right? So for example here you say, okay, 5 times in a row you're inside. And this is with the same interval length. So it could be, for example, a day. So 5 days in a row this event will occur. So I call this my period length. So it could be a day or 2 minutes or whatever it could be. And then I call this the offset. So that's the time from the start of time to when I start to measure my visits. Okay. So here I have 5 in a row, but maybe I have here I have 9 events, but only 1, 2, 3, 4, 5, 6, 7 of them are inside. So it's 7 out of 9. Right, that's still pretty okay, maybe. So I want to find, for any kind of these intervals, I would like to find the best regular pattern. Yeah?
How do you choose the number of days? For example, we change 5 to 9. Some intervals lay inside the period length, and some others go outside. And offset changes. How can you really mention these parameters?
Yeah, I'll talk about that actually. Okay. So let's look at the very simplest case. So I'm given the offset. So I know when you start. I know the first time you do this. And I know the period length. So this is by far the easiest case, right? So, because then this is fixed. Everything is fixed.
Just we have we make an scale for these intervals, or we just.
So I know when I start measuring, so the offset, and I know the period length here.
And we're going to measure in our period how much it takes being in, for example, in that popular place. Or
Now, so now I'm going to, I'm just going to try to find the longest subsequence where I have this repetitive behavior, right? Because it might be that I track you. I might track you for 5 years, but maybe during 1 year you go to play football every Sunday. So even though I know the period and I know the offset, I still want to find the longest subsequence when you perform this regular activity. Okay, so I can see this. So if the period length and the offset is fixed, then all these events are fixed. So the only thing I need to do is, okay, I'm outside, that's 0. I'm inside is 1, inside is 1, and so on. So what is the problem then? Well, the problem is, given a bit string S of length n, and say that I have this constant C that tells me how large proportion of the time I need to visit. Find the longest subsequence S prime of S such that there are at least a fraction of C of all the bits has to be ones. Right? That's the equivalent problem. Right? So, for example, if you go to play football for 1 year, that would be that I would find a subsequence of 52 bits, and then say you would try to go at least 75%, then C would be 0.75, and I would like to find that subsequence.
So even that roughly version of longest common subsequence?
How would you use the longest common subsequence?
I think it is solved by dynamic programming approach. Longest common subsequence sequence.
So, but what is the common subsequence?
Here you have only one sequence given, right? So
Yeah.
common subsequence, you have 2 sequences.
Yes. So what? How, you want to find, if the longest common subsequence, you have 2, and you want to find the longest subsequence that coincide, right?
I thought that because we just want to find a subsequence with longest length that only includes 1, so maybe that's...
No, so that would be if C is 1, then I require everything to be 1. But if I say it's enough with 75%, then...
So what is maybe a bit confusing that the notion of subsequence is maybe not the same, because you're not allowed to skip.
I'm not allowed to skip.
So the longest common subsequence, right? The subsequence is simply an arbitrary subset, you could say. And here the longest subsequence would simply be take all the ones and add as many zeros as you like until you get to. So the definition of subsequence is different.
Oh, okay. Okay, so this has to be a consecutive sequence. I cannot, my sequence cannot be that I do something and then wait another year or so, and then I continue the sequence. It has to be a continuous sequence. So I'll show you what I mean. Or maybe I don't. So what I want to find is just one continuous subsequence of my long bit string, such that if I look at this subsequence, then at least c, a fraction of c of them has to be 1. Yeah?
Sorry, for example, you're going to track, you start from today, and for example, every 10 minutes you go and check where I am. It shows the location of 0 and 1 for being inside this popular place or outside. Yeah?
No, that would give you, this would only give, so every 10 minutes it might be here. Right? But this says, so say I want to track that you do something with a weekly regularity. So say you play for 1 hour every Friday afternoon. Then I want, this is the Friday afternoon when you're playing football, and this is the Friday afternoon when you're playing football. Yeah.
And you do it during a long period. For example, you continuously track in a specific. And how can we? I'm thinking about we cut these segments in a specific time. For example, we have a long sequence each week, and then we track the common subsequence, as you said, to finding the similarity between the two groups.
Yeah, so you do this for 2 weeks. And what do you do then? So you get all these sequences, and then you would like to, because that's what you're saying, right? You get, so you're saying you track for 1 week, track for 1 week, track for 1 week, and then you do some kind of pairwise. Yeah, I guess you could do that. I don't know how fast it would be though, but I guess you could do it. Okay, so I want to find the longest consecutive subsequence such that at least a fraction of c of them is 1. Okay, so this is so the problem can be restated slightly. So I say I define a function fi, so it's just the sum of the bits from 1 to I. Right, so f of I is just the sum of the bits from the start to index I. Right? So now I want to maximize b minus a. So I want to maximize the horizontal sequence, so the number of bits, such that if I take the number of bits at this point in time minus the number of bits in this point of time, it has to be greater than c times b minus a. So at least a fraction c has to be once. Okay, so now I can just modify this a little bit, because, okay, so I have this increasing function, and I can just rotate it a little bit. Right, so I remove more or less the diagonal, c times I. And now, again, I want to maximize b minus a. So I want to maximize the horizontal duration. And I want to guarantee that g of b minus g of a is greater than 0, right? Because that's just saying that if I end with something that is higher than when I started with, then I will have at least c times I once there. Right? And this is just because I just removed c times I. So I know if it's positive, then it has to be greater than c times I. Okay. So this is what I have. But that means that if g of b, so g, the function value g of my right endpoint, and has to be greater than the function value of my left endpoint, then the longest sequence I can get, the right endpoint has to lie on the upper right envelope of my function. And g of a has to lie on the lower left envelope. I thought you did that yesterday. No. Okay. So, so what is the definition of upper right envelope? So it's, let's see. So it's the upper, everything that is above the curve that I can see looking from a point at infinity. Does that make sense? Yeah. So it would be this envelope here. Right? And similarly, I can define the lower left envelope. Right? As everything that is below the curve that I can see from minus infinity. And again, I only want to see to it that the function value of my right endpoint is greater than or equal to the function value of my left endpoint. Right? So I can walk along my lower left envelope, and then I can see how far to the right I can go. Now this is a decreasing monotone function, so if I continue walking, that means that I will only walk further along the upper right envelope. So I will walk here and I will walk here and I will try to see, and at each point I can see what is the longest consecutive subsequence. Right? So it's very simple, right? And this you can do in linear time. Right? So if I have fixed the offset and I've fixed the period length, then I can easily do this in linear time. Okay. And I can even do it in the compressed case. So if I don't get the bit stream, but I get, say, 3, if I have 3 ones, then I just model it as 3. Then I can do it in linear time with respect to k, using exactly the same approach. More or less. Okay, good. So this is a very simple case. If you start to look at other variants, which will become more interesting, then it will also be a bit more tricky. Right? So say your period length is fixed, but your offset is not fixed. Right? So you have your period length, but it can start and end in some area. You don't have this specified. So it turns out that this is equivalent to the following problem. I look at, so say I just cut all the periods, intervals starting from the start time. So I get this, right? So this is just taking all the intervals, putting them on top of each other. Okay, let's see how it looks. And now the question is, I want to find the longest vertical segment, A, such that at least a fraction C of the horizontal segments is intersects or inside. Right. So I think this is a very nice problem. So here, you just want to find the longest vertical line, and it could be anywhere. Right. And it turns out that you can do, we could do this in n to the 3/2 log n. But, maybe it could be done much faster than this. Okay. The most tricky case is, of course, if you don't have any offset and you don't have any period length. So now, you can start anywhere and your period length could be anything more or less. So the first observation is, if we look at the longest pattern, then we can translate it and scale it such that one of its visits has to coincide with the start point of an interval. Right. I mean, if you have an optimal solution, then you can just move it until one of the events will hit a start point of an interval. So you can use that to get a fairly bad bound, but at least a bound. So then you can do it. So in a first paper, it was shown you can do it in n to the 4, and then it was improved later on to n to the 7/2 log stuff. But this is still we have no. I mean, it should be possible to do much better than this. Okay. So if it's fixed, the offset and period length, then we can do it in linear time. If the period length is given, then we can do it n to the 3/2. You can also find a fairly good approximation in n log n time. If nothing is known, it's just n to the 7/2, which I'm sure must be possible to improve. Okay, and the open problem is, of course, to approximate. Improve the running times of all of them, or are there any lower bounds for any of these? Okay, so I'll just say I'll just finish off with a problem that I've been working on a bit in the last few years, last couple of years maybe. So it's in the most general statement, you were given a Euclidean graph G in the plane. So all the edges are straight line segments between the vertices. So we want to pre-process this graph into a data structure such that if we're given a query, so the query is just a polygonal path, and say a positive constant delta, then we want to report all the subcurves of this graph that has, say, small Fréchet distance, at the Fréchet distance at most delta to Q. Or if we want just to do the nearest neighbor version, just give me the subcurve of the graph that has smallest Fréchet distance to my query. Right? And the results we have for this, I think it's a really nice problem.
How about the inputs? You given the graph, or
I'm given the graph, yes, and now I'm allowed to pre-process the graph.
how about making graph? If we make a graph, the Euclidean graph that has a we can store the graph instead of storing all the curvature that are the same.
You want to make the graph instead? Maybe. Okay. And also the thing with because we're looking at the Fréchet distance, the subcurve that you report doesn't have to start and end at the vertex, which makes the problem much, much harder, right? So if you want to say just report everything. So what we use is the Fréchet distance. Yeah. So I'm sure that if you look at maybe some other distance measure, it could be a bit easier. So the first result we had was only for counting. And it's a pretty weak result. It just says that, say that your input is a polygonal path. So your graph is just a polygonal path. And you only allow queries to be segments. Right? Then we can approximate the number of subcurves along this path that lie within distance delta. Actually, we cannot even do that. We can only approximate roughly how many number of subcurves that lie within some constant within this delta. So it's a very weak result. And I think still we use quite a lot of nice techniques in the paper, but the bounds are just terrible. So I think this is a very nice problem. It's a very natural problem, I think. But there are hardly any results at all. Okay. So we improved this for a very special case last year. So if you assume that the graph is C-packed, then you can do a little bit better. So if you assume that you have a C-packed tree, right, then you can get a slightly better bounce. But this is only for C-packed graphs, or for C-packed trees, which is again very constrained. Okay. And again, the bounds are not great. I mean, this again must be possible to improve. Okay. Yep. I thought I had some open problems here, but I didn't put any. Okay, thank you very much. By the way, now when I'm here, and I know this is my last lecture, so I just want to thank the organizers. Thank you very much for incredible organization. It's been a real pleasure to be here. And it's taking a lot of work to prepare all the slides, but I think I will be very sad to see when the winter school is over, because it's been so nice to interact with all the students. It's nice to see such a enthusiastic community here in Amica Bewell, the whole of Tehran, more or less. So thank you very, very much for inviting me.